This lecture will be about one of the most important numbers in mathematics, the exponential or e. Unlike the number pi, which has a history that goes back 2000 years or more, e had to await its discovery until the invention of calculus some 300 years ago. Here are the first 50 digits of the number e. Actually, the most important thing about the number e is that it is associated with the exponential function. The exponential function deals with exponents. So let's first review what exponents are. Let's begin by asking ourselves what a number like 3 to the power 4 means. We've been told in school that this is 3 multiplied by itself 4 times. And in this particular case, it is 81. Well, what does this number mean? 2 to the power 1/3. That means that if I take 2 to the 1/3 and multiply it by itself 3 times over, that gives me the number 2. We also call it the cube root of 2. In general, if I have a number a, any number, and I raise it to the mth power, then this is a multiplied by a, etc., m times. Similarly, if I have a to the power 1 over n, and both m and n are integers, then the meaning of this is that if I take a to the 1 over n and multiply it by itself n times, then I am going to get a. So that's the way to define a to the power 1 over n. So what if I had something like this, a to the power m divided by n? Well, this means that this is a to the power m to the power 1 over n, or equally, it is a to the 1 over n multiplied by itself m times. And so this is the way to extend the understanding that we had over here and over here. But now let's move to something totally different. We know what a to the power m is, and a to the power 1 over n is, where m and n are integers. But what do I do about a to the power x, where let's say x is square root of 2 or something like that? In other words, how do I define something like a to the square root 2 or some other number which is not an integer? In this case, we will make a definition, and we will say that a to the power x plus y is defined. So I am going to put a definition over here. A to the power x plus y is defined as being a to the x multiplied by a to the y. Of course, I could write it as a to the y, a to the x, but that's the same thing. So here's the definition. Now you can see over here, for example, that it's consistent with what we've learned above. If I have 3 to the power 6, let's say, that's 3 to the power 4 plus 2, and you could easily write this as 3 to the power 3 plus 3, etc. And so this is going to be our definition, which will be very useful, and this holds for x, y, any two numbers. So they don't have to be integers anymore. Okay, so now from a to the x plus y equals a to the x, a to the y, I'm going to get some consequences. First of all, let me put y equal to 0, which means that a to the x plus 0 is a to the x, a to the 0. Now a to the x plus 0 is a to the x. So I have from here that a to the x is a to the x, a to the 0. And if I divide both sides by a to the power x, then obviously I arrive at the conclusion that if I raise any number to the power 0, the answer is 1. It doesn't matter what a is, a to the power 0 is 1. Now, what does this say when y and x have opposite signs? This says that a to the x, and now instead of y over here, I'm going to put minus x. A to the x minus x is a to the x, a to the minus x. And now on this side, I have a to the power 0, so that's 1 from here. And so what I've proved is that 1 is equal to a to the x, a to the minus x. In other words, we've arrived at this important result that if I take any number to the power minus x, it's 1 over that number to the power x. And these are two important conclusions, this one and this one. I've just rewritten those results more cleanly over here. And now let me remind you once again that a function is a machine which takes an input and gives you an output. This takes us to the exponential function, the function which is the real subject of this lecture. You give this a number x, and out comes e to the power x, where e is that marvelous number that we've just talked about, 2.7, etc. The basic definition of the exponential function is here. In words, this says that if you differentiate the exponential e to the x, then you get back that same function. So if I was to write f of x equals e to the power x, then this equation can be rewritten as df by dx is equal to f itself. And so you can either take this or this as the definition of the exponential function. Let me quickly review what we've learned so far. First of all, that e to the x plus y is e to the x multiplied by e to the y. And that's because of the definition that we had earlier. Now, there's one thing that I should have said earlier, but it's not too late even now, that e has to be a number that is positive. Else we would get a negative number to some exponent, and we'll handle that at some later time. But we shall put as a requirement that e be a positive number, in which case e to the power x also has to be positive. Now, mind you, we don't know the value of e as yet, but we will find out. And of course, e to the power 0 is equal to 1 because that's true for any number. Now, using just the fact that the derivative of the exponential has to be the exponential, that is a definition. Using that, we will make some important deductions. First of all, that all the derivatives of the exponential are positive. And that's actually very easy to see, because if f of x is written as e to the power of x, then f prime from here has to be f itself. In other words, if I differentiate the exponential, I get back the f exponential. Now, what about the second derivative? The second derivative is the first derivative of the first derivative. The first derivative f prime is f, so that's f prime, but f prime is equal to f, so f double prime is equal to f, and that's positive. What about f triple prime? Well, that's equal to f also, and so all the derivatives of f. So the nth derivative is equal to the exponential itself, and the exponential is positive, as was said earlier. Now that's a very important conclusion, because it's saying that the graph of the function is always sloping upwards. So if I was to make a little plot like this, here is e to the power 0, which is 1. It's got to go up. And this brings us to the second point, that e to the power x increases monotonically with increasing x. A monotonic function, let me just draw one over here. Let's say that here's a function that's increasing. That's a monotonically increasing function. Here's a function that's monotonically decreasing. It's always decreasing. On the other hand, a function like this is not monotonic. It's neither always increasing nor always decreasing. Anyway, let's come back to the fact that e to the x increases monotonically. Why is that? Because the first derivative, f prime, is always positive, which means that the exponential is always sloping upwards. It's never going to have a maximum and come down, because at the maximum f prime would have to be 0. It's now time that we learned how to differentiate exponentials with various arguments. Let's first of all recall that the basic definition of the exponential function is that the derivative of e to the x is e to the x itself, together of course with e to the 0 being equal to 1. Of course, some people prefer to write this as e to the x dash or prime is equal to e to the x, but these two are completely equivalent to each other. Now, let's avoid common mistakes. Students sometimes write d by dx of e to the, let's say, 5x as e to the 5x itself. But that cannot be true, because look at the defining relationship. It says that the derivative of e to the x with respect to x is e to the x itself. Here, one must use the chain rule, and the proper answer, so this is wrong, the proper answer is that d by dx of e to the 5x is 5 times e to the 5x. Similarly, it would be wrong to say that d by dx of e to the minus x is e to the minus x. That too is wrong, and the correct answer, again by using the chain rule which you learnt in a previous lecture, is that this is equal to minus e to the minus x. Well, let's now work out some more complicated examples. So, what does one do about d by dx of e to the power x squared? From the chain rule, this is the derivative of the exponential function evaluated at the argument x squared, so it's e to the x squared. But now one must differentiate x squared as well, so this is e to the x squared into 2x, and that is the correct answer. What about, let's say, this, d by dx of e to the x? Well, again, when you differentiate the exponential, you get the exponential itself, and the argument of the exponential will be e to the x itself. So this is e to the x. But now one needs to differentiate e to the x itself, and so that's e to the x. And of course, now one has a lovely relationship that if I have d by dx of e to the x, etc., and of course one can keep going over here, well, that's going to be quite funny. it's this, and then we need to differentiate this, so that's e to the x, and then we need to differentiate this, that'll be e to the x, and then we need to differentiate this, so that's e to the x itself, and that is the final answer. Here is something that's very important. The exponential function grows faster than any power of x. Let me come back to this slide once I show you some graphs. Let's first look at this graph over here. There are going to be three functions plotted on it simultaneously. So here is x squared, which is growing with x but quite slowly. Here's x to the power 4, which is growing relatively much more rapidly. And here's e to the x, which lies between x squared and x to the power 4 for this particular value of x, which is a little more than 6 and a little less than 7. Now, let me increase the value of x. You see that x squared is growing but slowly. X to the 4 is growing, but the exponential is growing even faster, and at this point, which is less than 9, bigger than 8, they are equal, and now the exponential has 1. Let me repeat with two other functions here. Here's x to the power 4, and here's x to the power 6. E to the x lies in between them, and that is for a value of x which is around 16 or so. But now let me increase the value of x, and you see that the exponential is rising very fast. It has now defeated x to the power 6 and is now off the screen. Let's now come to this claim that the exponential function grows faster than any power of x. Now this is extremely interesting, and it's extremely important. What this is saying is that a function, the exponential, is growing very, very fast, and it's growing faster than x to the power, let's say 100 or even 1,000 or even 1,000,000. Mathematically, what we mean to say is that e to the x becomes much, much bigger than x to the power n for any value of n, provided that x is large enough. Now, another way of saying this is that the limit as x tends to infinity of x to the power n divided by e to the x is 0. Now clearly, if you put x equal to infinity, this is then infinity divided by infinity, and so that's meaningless. Let's therefore go to L'Hopital's rule. And in L'Hopital's rule, you remember that you differentiate the numerator and the denominator. If that gives you a limit, then fine, you stop there. If it doesn't, you differentiate again, and you keep differentiating until you arrive at the limit, if that limit exists. So let's take the derivative of x to the n. That differentiated once will give us n times x to the n minus 1. If I take the derivative of the denominator, e to the x, that gives me e to the x. In other words, the derivative of this is e to the x. Why? Well, that's the definition of the exponential. Now, clearly, this is not good enough, because as x goes to infinity, the numerator is infinite, so is the denominator. So we go to the second differentiation, in which case we will get n into n minus 1 and x to the n minus 2 over, again, e to the x, because if I differentiate e to the x, again I get e to the x. So the point is that when I differentiated x to the n, I got 1 power less. When I differentiated again, I got 2 powers less. And let's say that n is 1,000. If I differentiate x to the 1,000 times, then eventually I will get a number which is some big number, but whatever it is, divided by e to the x. And now e to the x goes to infinity, and so the limit is 0. Using L'Hopital's rule, we have proved that the limit of x to the n over e to the x is 0, and hence the exponential function grows faster than any power of x. Let's now apply what we've learned about the exponential function to population growth. Let n be the number of people in a country. And of course, n changes with time. It's a function of time. The rate at which the population is increasing depends upon the number of people who are actually living at that particular time. So dn by dt is proportional to n. If we want to convert this into an equality, then dn by dt becomes some constant times n. That constant we're going to call lambda. Now clearly if lambda is 0, then the population is not changing with time. If lambda is large, then the population is changing rapidly with time. So it depends upon how many children a couple have, etc. Now the solution for this, I claim, is n equals n naught e to the lambda t. Let me check. Let me take dn by dt from here. Well, that's n naught. And if I differentiate e to the lambda t, I get lambda times e to the lambda t. But n naught times e to the lambda t is lambda n itself. And so this is the correct solution to this equation. How does one understand the result? At t equal to 0, we have n at t equal to 0 is n naught e to the 0, and e to the 0 is 1. So n naught is the number of people at the starting time. So let's make a little plot. Here is n, here is n naught, and this number n is increasing very, very rapidly, and it will go to infinity as t goes to infinity. Now, of course, in a finite population, you can not have infinity, but you can have very, very large numbers, and so population growth can be a very serious problem. We'll now take a slightly less serious problem. Here's a cat on a hot water bottle. The cat wants to know how fast the bottle will cool. So she wants to know what t is as a function of time. She's been told that the rate at which the bottle is cooling is proportional to how hot it already is. A hot bottle will cool faster. But here, the rate of change of temperature is negative. In other words, the rate is decreasing. And if we want to convert this into an equality, then again we write dt by dt equals minus some constant lambda times t. Of course, if lambda was exactly 0, then the temperature would never change with time. The bigger the value of lambda, the faster the hot water bottle will cool. The solution of this equation is, one can see, t of t equals some constant t naught e to the minus lambda t. Let's check to see if this is right. Well, if you do that, dt by dt is t naught, and when we differentiate what's this exponential over here, we get minus lambda e to the minus lambda t. And now you can see this is just minus lambda, and t naught e to the minus lambda t is this itself. And so we've checked that this is the solution to this equation. Now clearly, when t is equal to 0, in other words, when this hot water bottle has been filled up for the first time, then t of 0 will be t naught. So this t naught over here tells you what the temperature will be at the very beginning. If you make a plot of this, then the temperature is going to come down and it will decrease all the way to whatever that final value is, which is 0 in this case. So if it's freezing, then eventually this temperature will go down to t equal to 0. So far, the only thing that we know about the exponential function is that the derivative of the exponential is equal to the exponential itself. And of course, that e to the power 0 is equal to 1. Now, I claim on the basis of the above that the exponential e to the x can be written as 1 plus x plus half x squared plus 1 over 3 into 2x cubed plus 1 over 4 into 3 into 2x to the fourth, and that this can and must keep going on forever. Let's see if this is indeed correct. So as a check, I'm going to take the derivative of what is above, so d by dx of the above. From 1 I get 0, from x I get 1, from here I get x, and the derivative of x cubed is 3x squared, so I get half x squared. The derivative of x to the 4 is 4x cubed, so we get 1 over 3 into 2x cubed, and this goes on forever. In other words, if we add up all of these terms over here, that's the same as what's up above, and we get e to the x. In other words, this series for the exponential is indeed a way of writing e to the x. Now this is very nice, because if I want the value of e, then I put x equal to 1, and I get 1 plus 1 plus 1 over 2 plus 1 over 6 plus 1 over 24, etc. And if you add this all up, you get 2.71, etc. This is a way of getting the value of e to the x for x equals 1, but it is also useful for getting the value of x for almost any number x. In this lecture, we understood the exponential function rather well. In the next lecture, we're going to talk about the inverse of the exponential. And mind you, the inverse of e to the x is not e to the minus x. It's going to be the logarithm. But that's for the next lecture.